Hi everyone, this is an anatomy and physiology video for healthcare students. In this video, we're going to talk about some basics, acids, bases, buffers, and the pH scale. So when we're thinking about acids and bases are considered to be inorganic compounds. Inorganic means that they typically lack the carbons and hydrogens in long chain form that we see in organic molecules like carbohydrates and proteins. So we still release these in our bodies. It's just that they are not made of those long chains of carbons and hydrogens. Instead, we classify them based on what they release in water or in solution. So acids typically release hydrogen ions in solution, while bases release hydroxide ions in solution. A shortcut method to figuring out what you're looking at, often acids have a hydrogen or several of them at the beginning of a compound, whereas bases will have some hydroxides at the end of the compound. So if you're not familiar with reading chemical formulas, that may help you do a little shortcut method in figuring out what you're looking at. So in looking at some examples in the human body, acids would include things like stomach fluids, which are really acidic. On the pH scale, they're around 1 or 2. Vaginal fluids, saliva, urine. Urine is an interesting case because it ranges from acid to base. So in many cases, if we've had a recent meal that's protein enriched, then you'll see that urine be on the acid end of the scale. Now, in terms of taste, as human beings, we actually prefer acidic, tart foods to the bitterness that comes from bases. All right, now let's talk about bases. So in the human body, we're looking at blood with a pH of around 7.4, semen or pancreatic fluids. So we're really going to focus in on blood because that is an important one for us to maintain. It needs to be close to 7.4 for us to be able to survive. So kind of interesting to note that we do not prefer the taste of bitter bases. In fact, many household chemicals happen to be basic or alkaline, and certain medicines, to make them unpalatable, are actually made to taste bitter. So, if you try to chew up a pill, then it often has a bitter taste to it, or even some medications that otherwise may not taste so bad have a bitter taste added just so that we don't stand there and guzzle the whole bottle. So let's apply what we've learned about the acids and bases to the pH scale. On the pH scale, we're looking at a range of 0 to 14. This is a logarithm-based scale, meaning that every whole number you move is a 10-fold change in acidity or alkalinity. Notice that neutral number there, 7, is equal amounts of hydrogens and hydroxides being released. Water is probably the best thing that we would put at that 7.0 neutral. Once you drop down to 6.9, you're in acid territory. Once you rise to 7.1, you're in alkaline territory. So the extreme ends here are where the strongest acids and bases are situated. As you move toward 0, you're dealing with the strongest acids, or toward 14, you're dealing with the strongest bases. So let's take an example. Let's pick on the number 3. So 3 is going to release more hydrogen ions than hydroxide ions. 3 doesn't release absolutely no hydroxides. It just releases far more hydrogens than it would hydroxides. On the other end of the scale, let's pick something like 11. So a pH of 11 is basic. It's going to release more hydroxide ions than a pH of, say, 3 would. So it's a continuum more than just a hard, fast changeover at 7 from whatever that chemical releases. So let's look at some examples. We know that every whole number you move on the pH scale is a 10-fold change. So a pH of 4 compared to 5 is a 10-fold change. 4 is 10 times more acidic than 5. Otherwise, you could flip-flop it and say 5 is 10 times more basic than 4. So you never have to work with negatives here. You can just flip-flop those numbers and rearrange your sentence. You're always going to be able to deal with positive numbers. We can also say pH of 4 is 100 times more acidic than 6. Flip-flop it and say that 6 is 100 times more basic than 4. I hope you caught that we are looking at 100 times difference here, not 20. That's because every whole number you move is tenfold change in acidity or alkalinity. And so if you move multiple numbers, you're going to be multiplying 10 times 10 for every whole number that you move. So that's why it's a 100-fold change in acidity or alkalinity, not 20. Okay, so let's work through a shortcut method. The very first question says a pH of 10 is how many times more basic than a pH of 8? So if you're familiar with how to work the pH scale, from 10 to 9 is tenfold. 9 to 8 is another 10, so you would multiply that and get 100 as your answer. Now, there's another way to work this, and you can simply take your two pH values that you're comparing, subtract them, that gives you 2. But hang on, don't stop yet. Take that 2, that's the number of zeros you're going to put behind the 1. So it's a 100-fold difference. Or you can use that 2 as a superscript. It's 10 to the power of 2. So, of course, that also works out to be 100. So yeah, there are multiple ways to get the right answer. If you get tripped up multiplying tens, you can always try this little shortcut method. Okay, so let's take number 2. Number 2 says a pH of 4 is how many times more basic than a pH of 2. So keep in mind, we're dealing with acids, but 4 is heading more toward the alkaline end of your pH scale than 2. So we could say that 4 is 100 times more basic than a pH of 2. All right, so 9 and 7 for number 3 here, those are both bases. So here it really does make sense when we say that 9 is how many times more basic than 7? Also 100 times more basic. So even though 7 is a neutral number, we're still comparing two values on the pH scale. And yeah, 7 releases some hydroxide ions, but 9 releases 100 times more. Give you a moment to think about this last one. A pH of 12 is 100 times more alkaline. That means it's more basic than what number on the pH scale? It's 100 times more basic than 10. All right. Just as a side note, acids and bases can combine together to create neutralization reactions. This happens in our bodies all the time. Acids and bases react, and what we end up seeing as the result is salt and water. So this is kind of leading us into another conversation having to deal with buffers. So buffers exist in our body to help prevent drastic pH changes. We have a number of very important blood buffer systems, and their job is to prevent your pH from yo-yoing. The pH needs to maintain around 7.35 to 7.45. On average, that should be around 7.4. We run into issues with homeostasis if we get outside that range. So we want to make sure that we stay close to 7.4. So the way buffers work is either they will accept hydrogen ions when needed to pull them out of the blood pH, or they can donate hydrogen ions when needed to make the blood become more acidic. So they're kind of like sponges in a way. They can squeeze out hydrogens to make your blood more acidic, or they can soak them up to reduce the acidity and make your blood more alkaline. Okay, so let's talk about an example. I'm just using a pH of 8 here as our example. This doesn't have to be blood, for instance. This could be any beaker full of a solution with a pH of 8. And if it's our goal to stay around 8, we're going to see how that buffer plays a role in maintaining the pH. So let's add an acid. Let's say we've got a pipette, a syringe, whatever. We're going to add some fluid that contains pH 2 to our solution. That dropped our pH to 6. Well, our goal was to stay close to 8. So this definitely had an impact on pulling our pH down. So how can we maintain pH closer to 8? Well, let's add a buffer to that beaker. So this time, when you add a pH of 2 into the solution, the buffer maintains that pH. So like we talked earlier, the buffer acts like a sponge. It can soak up and accept hydrogen ions, which are protons, or it can donate them. And in this case, we actually see the buffer accept those hydrogen ions. That helps to minimize the impact of the pH change, and we stayed closer to where we originated, which is around a pH of 8. So here are some practice problems for you. You may want to pause the video, take an opportunity to answer these questions, and then we'll do the answers when you're ready to restart that video. Okay, so for number 1, a pH of 2 is how many times more acidic than 4? It is 100 times more acidic. All right, number 2, a pH of 6 releases 1,000 times more hydrogen ions than a pH of 9. So on the pH scale, the lower the number, the more acidic that solution. A pH of 10 is 100 times weaker than a pH of 12. Is it a weaker acid or a weaker base? It's a weaker base, right? So in terms of on that end of the pH scale, we're dealing with those bases. You know, you could also say that 10 is 100 times more acidic than 12. So number 4 there, we've got a pH of 8 releases 1,000 times more hydroxide ions than 5. That's because as we go up the pH scale toward 14, those numbers are going to release more hydroxide ions the higher you go. So every number you move, it's 10 times more. For number 5, a pH of 3 releases 10 times more hydroxides than a pH of 2, and that's because we're going up the pH scale toward 14. And then finally, a pH of 12 is 100 times more alkaline or basic than a pH of 10. Well, thanks for watching. If you enjoyed the video, please like it or consider following my channel. If you have any questions, you're welcome to leave them in the comments.